So today, week 17, we're going to discuss chapter 1, chapter 2, and chapter 4 questions. Yeah. Cool. Let's get into the first question. 1A. Bromine has two stable isotopes, bromine 79 and bromine 81. By comparing the number of subatomic particles of these isotopes, explain what is meant by the term isotopes. So you got to read the question carefully. It's not just defining isotopes, but need to compare, yeah, using bromine 79 and bromine 81. Okay, so we can give the definition and then you need to make comparison with the two isotopes. Isotopes are atoms of the same element with the same number of protons but different number of neutrons. So taking into account isotope 79, so bromine 79 has 35 protons and 44 neutrons. Let me correct a little bit. Okay. And bromine 81 has 35 protons and 46 neutrons. So in exam, you'll be wondering where you get the 35 protons. You can refer to the list of constant. Okay, list of constant of selected elements. The table of RAM. List of constant table of RAM of selected elements. So you can find proton number for bromine 35. So 79 minus 35, 44, that is neutron. Because nucleon number, this is nucleon number, yeah, the superscript is the sum of protons and neutrons. Okay, so do not panic during exam. You just have to look out at the table of RAM for selected elements. So after counting the number of protons and neutrons, obviously protons are the same, neutrons are different. So it complies the definition. Isotopes are atoms of the same element having the same number of protons but different number of neutrons. Okay, part 2. Determine the number of electrons of bromide ion. Bromide ion 36 electrons, because bromide ion Br negative. The number of protons 35 in neutral bromine. So bromide, in neutral bromine 35 protons, 35 electrons. Okay, neutral bromine got 35 protons, 35 electrons. So in bromide, proton would still be 35, but the electron will be 36. That is why the charge is negative. Yeah, means electron is added, to the atom. Okay, so in the formation of ion, remember what is moving in and out of the atom is electron. So electron will change in number, whether it forms anion or cation. Okay, the number that changes is the number of electrons. Proton is always constant. So the answer is 36 electrons. And the marks, you can mark your own script. 1 mark for definition, 1 mark for counting the protons and neutrons in both the isotopes, and 1 mark for the answer for A2, 36 electrons. Okay, question 1B. In a complete combustion, 1 gram of W was burned to produce 2.52 gram of carbon dioxide and 0.443 gram of water vapor. Determine the empirical formula of the compound. So this is combustion data. From carbon dioxide, you can calculate the mass of carbon. From water, you can calculate the mass of hydrogen. So mass of carbon using carbon dioxide data, 2.52 divided by 44 means you are converting it to mole of carbon dioxide. And in 1 mole of carbon dioxide, there's 1 mole of carbon, which is 12 gram. So 2.52 divided by 44 is actually the mole of carbon dioxide. Multiply by 12 gram, that is per mole, got 12 gram of carbon or 1 mole of carbon. So you get the answer. That means this is a 12/44 is a fixed ratio, yeah? Ratio of carbon to carbon dioxide. For hydrogen, you need to look into water. 0.443 gram divided by 18, that means you are converting that mass into mole of water. And in 1 mole of water molecule, you can see 2 mole of hydrogen, which is 2 grams. So you multiply by 2. So that will give you the mass of hydrogen. So there's one more element, yeah, oxygen. So to get the mass of oxygen, you just take the mass of sample minus of the mass of carbon and hydrogen. Okay, this is mass of sample minus of the mass of carbon minus and mass of hydrogen. So what is remaining is the mass of oxygen. And the next step, you tabulate, yeah? Tabulate your answer. So as usual, list out the elements, then mass in gram. So you just take from what you have calculated, put into the table, then calculate the mole for each element, divide by their respective RAM, yeah. And then to get the simplest mole ratio, you divide, you see these 3 moles there, which is the smallest. This is the smallest. So all these 3 mole figures here need to be divided by 0.0165. Okay. So we get 3.47 for carbon, 2.98 for hydrogen, 1 for oxygen. And we cannot round off here because this is too far away for rounding off. So we multiply with a number until we can round off. Yeah? So all these figures we multiply with 2. After multiplying with 2, you see the results all can be rounded off. Yeah? 0.9. So can be rounded off to 17. This also 0.9 to 7. Sorry. 5.96 round off to 6 and 2 is 2. Yeah? So that is the simplest mole ratio, 762. Therefore, the empirical formula is C7H6O2. All right. So we are done with this. The question just asks empirical formula. Let's move on to question 1C. Calcium acetate solution. So the formula of calcium acetate is given CaC2H3O2 bracket 2 is the substance used for reducing phosphate level in late stage kidney failure. In an experiment, 250 ml of 0.25 molar calcium acetate solution was prepared. Determine the molality of the solution with a density of 1.509 gram per ml. Okay, so you are given this. This is actually volume of solution. Okay, what you want to find is molality. This is your task. Besides that, you are given density. Yeah? Okay, density, we use the symbol rho. Yeah? Density is of solution. So molality, the formula is mole of solute divided by mass of solvent in kilogram. So you have to observe what is needed, yeah, for the task, to solve the task. Okay, so the solute is calcium acetate. You need to get the mole of it. Yeah, you are given the volume and the molarity. So you have to work for the mole of solute. Just by using these two data is enough, yeah? Volume and molarity, you can find the mole. After getting the mole, find the mass of solvent. Okay, by using density, yeah, you need to find the mass of solution. After getting the mole of solute, you can find mass of solute. From density, you can find mass of solution, yeah, because density is mass upon volume, also of solution. So once you have found mass of solution, and you have already found a mole of solute, then convert to mass of solute. You take the mass of solution, you minus the mass of solute, you get a mass of solvent. All right, so that's how you go about. So the first we calculate mole of solute. Remember, this is solute, yeah? Solute is calcium acetate. Okay, if you got molarity and volume, you just take the molarity, multiply with the volume in liter, yeah? You write the unit properly, you will see cancellation of units, yeah? Leaving behind mole, so you're on the right track. Then you find the mass of solute by multiplying with the molar mass. This molar mass you have to calculate yourself, yeah? This is molar mass. Molar mass you have to calculate using this formula. Calcium acetate CaC2H3O2 bracket 2. You get 158.1 gram per mole. Okay, so you mole multiply by gram per mole. What is there behind is gram. So now we will look into density formula, which is mass of solution upon volume of solution. So from here, density given directly in the question, volume of solution given directly, 250 ml. So cross multiply, you get mass of solution. Okay, so density 150 gram per ml given here. 1.509. 1.509 gram. 1.509 gram per ml. And volume of solution is this 250 ml. So upon cancellation of units here, per ml and ml cancel, leaves behind gram. So this is mass of solution. Okay, look at your target, yeah, or your task. What you want is mole of solute, which is already here. Okay, mass of solvent, we need to calculate. Yeah, we have mass of solution, we have mass of solute. So mass of solvent, you take mass of solution. Mass of solution minus mass of solute. Okay, so you will get mass of solvent. Because in any solution, mass of solute plus mass of solvent is a mass of solution. So since you know mass of solution and mass of solute, just subtract and you get mass of solvent. So this mass of solvent is in gram. And molality formula, you need to convert to kilogram. Yeah? So just divide by 1000. So write out the formula first. And then substitute. You see, when you write formula, you include the unit. So you remember to convert the unit, yeah? From gram to kilogram, just divide by 1000, you get this. This is further rounded off, yeah, because too many numbers. Okay, too many figures here. 367.37 divide by 1000. So it's 0.367. 37 can be rounded to 4. Okay, so you're done. Molality is found 0.17 mole per kilogram. Okay, there's one more question, part D. Magnesium hydroxide is an antacid that is used to relieve indigestion, sour stomach, and heartburn. Okay, normally when you have gastritis, yeah, whatever medication given to you contains magnesium hydroxide. Yeah. Okay, so that's the beauty of learning chemistry, you see. It can be prepared by reacting magnesium chloride and sodium hydroxide with the byproduct of sodium chloride. In an experiment, a student allowed 15 per 1 gram of magnesium chloride to react with 9.35 gram of sodium hydroxide. Calculate the mass in gram of magnesium hydroxide that could be obtained at the end of the experiment. Okay, so you need, this is under stoichiometry, yeah, where you need to use balance equation, yeah, to solve. And magnesium hydroxide is the product, so you need to inspect the equation later. Okay, when we are dealing with equation, we always read equation in mole. For that reason, we convert these two masses, yeah, given here into mole first. Just be divided by their respective molar mass, which you have to calculate yourself, yeah, MgCl2 95.3. Just refer to the table of selected RAM of selected elements, yeah. So you sum up, you get 95.3. Okay, so units written here to show or prove to you that, yeah, finally the unit left is mole, yeah, because the gram can be cancelled. 1 over per mole, yeah, is mole. Same goes to sodium hydroxide. Divide by the molar mass. And then write a balance equation. All equation in chemistry must be balanced. Yeah? Do not present unbalanced equation in your answer. Anywhere where equation is concerned, always must present a balanced equation. All right. So we're going to find limiting reactant. When at the start, yeah, there's a certain amount of both reactants given. And now you want to relate with product, yeah? So you need to find out limiting reactant, even though it's not stated directly in the question. Because you will have problem if you don't find limiting reactant. Are you going to relate MgCl2 with magnesium hydroxide, or are you going to relate NaOH with magnesium hydroxide? So when you have that uncertainty, you know you need to find limiting reactant. Okay, so now we work out for the limiting reactant. So from the equation, you relate, yeah, the mole of magnesium chloride and sodium hydroxide. 1 mole to 2 mole. Just read the equation, yeah? 1 mole magnesium chloride equivalent to 2 moles of sodium hydroxide. So now the magnesium chloride, yeah, provided is this much. So just take this number times 2 over 1, yeah? You get this 0.316 mole. So now you see NaOH available or given this much. And based on the balance equation, this also NaOH. This is the requirement. Yeah. Theoretically, you need this amount. But practically available or given this amount to react. So you compare the available amount and the required amount. It looks like the available amount is less than the required amount. That means it's not enough. Yeah. What is given is not enough to react. So what you do now, you write mole of NaOH available less than required. Okay. So when the available is less than required, means what is given is not enough to react. That means NaOH is limiting reactant. NaOH is the limiting reactant. Okay, since you know already limiting reactant is NaOH, and now you want to find, yeah, the mass of magnesium hydroxide, which is the product. So you're going to relate this with this, yeah. Okay, remember every time when you want to find how much product is formed, you have to relate it with the limiting reactant. So again, read the equation. 2 moles of NaOH equivalent to 1 mole of magnesium hydroxide. The NaOH available or given, you must use this value, yeah? Okay? You must not use this value because this is theoretical. This is practically available or what is given to react, yeah? So you use this value to calculate the mole of magnesium hydroxide. Okay, so the equivalent mole of magnesium hydroxide is this number 0.234 divided by 2 or times 102. Yeah, so you get this is the mole of magnesium hydroxide form. Okay, remember always use the given or available amount, yeah, to calculate the amount of product. But the question is asking for mass, yeah, in grams. So after getting mole, no problem, just multiply with the molar mass. Again, you have to calculate this on your own based on the formula. So the answer is 6.82 gram. Okay, so 1 mark each. Every time before you conclude, which is the limiting reactant, give a brief explanation. Before deducing the limiting reactant. This is the explanation. Available less than required or available more than required. If available is more than required, means that particular reactant is in excess. So the other reactant will be limiting reactant. All right. So the total marks for question 1 is 21 marks. And this is also the total marks in PS1. In your final exam. Question 1, 21 marks. Now let's move on to question 2. Question 2 is atomic structure. The line spectrum of hydrogen atom in the visible region is shown in the following diagram. Name the series of the line spectrum. So this is just a simple knowledge question. You must have knowledge which series falls in visible region. You have Lyman, Balmer, Lyman. Wait, I better write it somewhere here. You have Lyman series, and then you have Balmer series. After that, Passion, bracket, BRA, BRACKET. Okay, and Fun. Alright. So Lyman is in UV region. This is visible region. These are all knowledge. Visible. And these three are IR. Infrared. So very simple. This is just a knowledge question. You must have knowledge. Visible region refers to Balmer series. So the answer is Balmer series. And then question 2, sketch an energy level diagram of hydrogen atom for the formation of line X. Actually, line X is line number 2. This is line number 1. This is line number 2. That means this spectrum is recorded from left to right. Because spectrum sometimes is read from right to left. How do you know to read from left to right or right to left? Very easy. You see the lines that separated very far apart from each other. That's where you should start off as line number 1. Okay. Line number 1 is always having a very big gap from line number 2. And then it gets closer and closer. Because spectrum can be read from left to right or right to left, depending on how it is recorded. Okay, so I erase this in order not to interfere the drawing. So this is the so-called energy level diagram. You have to draw lines, and first thing, just as reminder, you have to refresh what you have learned. The lines are getting closer and closer. Actually, every line is a shell. This is an enlarged portion of a cross-section of atom. Cross-section of atom nucleus here. Then you have this. Okay. The first and second shell very far apart. And then it tend to get closer and closer and closer and closer. Okay, so we imagine they come in the form of circles, shells. So this is n equal to 1, n equal to 2, n equal to 3, and so on. So the lines are getting closer and closer, because the shell are getting closer and closer. So when you enlarge a portion of this cross-section of atom, you also have to consider putting the lines, n equal to 1, n equal to 2, separated furthest away one from another. This one closer, and then it becomes closer and closer. So that's the thing that we have to remember, and that's what we look into. The first thing. Okay, draw the lines, put the label of the energy level, the shell number. Make sure the lines are closer and closer, further away from nucleus. And then label the energy. This means energy increasing. And line X is line number 2. Okay, you know Balmer series. You can use this, line number equal to N2 minus N1. N1 is something fixed, that you must know, your knowledge. Balmer series N1 equal to 2. If your line number is line number 2, okay, so to get line number 2, this one must be 4. 4 minus 2 equal to 2. So the N2 equal to 4, the N1 equal to 2. N1 is fixed based on the type of series, whether it's Lyman, Balmer, Paschen series, and so on. Paschen bracket, and so on. Okay. So, in other words, N2 is line number plus N1. Okay. N2 equal to line number plus N1. Line number plus N1. Line number 2. N1 Balmer series 2. So 2 plus 2 equal to 4. So the transition is from level 4 to level 2. So this arrow is transition arrow. Okay, showing the electron fall, from shell number 2 or energy level number 2 to energy level number 4 to energy level number 2. Okay, so that's answering this question. Energy level diagram for the formation of line X. That means you are showing the transition arrow, from where to where the electron falls. And then explain. Line X is produced when an electron falls from n equal to 4 to n equal to 2, and photon of energy is emitted in the form of light. So for marks here, mark for part 1 Balmer series, and then transition arrow correct 4 to 2, 1 mark. And then energy label, this is labeled, and correct energy level starting from n equal to 1, 1 mark. That means you label all this. And the last is the explanation. The important thing in your explanation, electron fall from where to where, and then energy emitted. That correspond to the line in the spectrum. This is the line in the spectrum. Okay, if you have any question, you can just on your mic and speak. If you do not want to use this formula to determine from where to where, you just, can manually count. For first line, it should be, because Balmer series, electron must drop to level 2. Yeah, this is for sure. So line number 1 is from the nearest, 3 to 2. So line number 2 should be 4 to 2. Line number 3, 5 to 2, and so on. You can also count manually to know from where it dropped. Okay. So first line is always from the nearest energy level. Second line, third line, and then just go on. If you don't use this is not what you call official formula. This will just help you to calculate. If it's line number 2, actually no problem. We can do it manually, like, just roughly scribble on energy level diagram. But if the line number gets bigger, probably this is more of help. Line number is N2 minus N1. So N2 is line number plus N1. N1 is your knowledge. If you don't have knowledge about N1, then nobody can help you. All right, so let's move on now. Part 3, calculate the wavelength correspond to line X. So just now line X formed due to transition of electron from n equal to 4 to n equal to 2. So to calculate wavelength, there are only 6 formula here that you learn for calculation in atomic structure. The one with wavelength, Rydberg's equation. Lambda equal to RH 1 over n1 square minus 1 n2 square because you know the n1 and n2. And Rydberg's formula, when you write, you have to indicate n2 larger than n1. Why? Because lambda is a measure of length. It cannot be negative. It wouldn't take a negative value. So to ensure you always get a positive value, n2 must be larger than n1. So between 4 and 2, n2 is 4, n1 is 2. Smaller number, n1, bigger number, n2. That would definitely give you a positive answer. Okay, the next step is substitute. You be very careful with RH. In your list of constant, there are 2 RH given. Because lambda is a measure of length, so the RH must be length measure, m minus 1. The other RH is in energy, joule. Yeah, you have 2 RH. In your list of constant, you can check. The other one is 2.18 times 10 to power of negative 18 joule. So you cannot use this when you are using Rydberg's equation because lambda is a measure of length. So you must take this value, length measure. All right. So you actually get an answer here. If you want to write the answer here, it's okay. But what the question wants is lambda, wavelength lambda. So after getting this is called wave number. Wave number, the unit is per meter, sorry. Then you just take the reciprocal of this value, you get lambda. Okay, since the question does not specify the unit, you can leave your unit, the answer in meter unit, or if you want to convert to nanometer, it's also not a problem. Okay, so remember what you have calculated directly is 1 over lambda. This value is 1 over lambda. Wave number. So to get lambda value, you take 1 over this value, or reciprocal of the wave number is the wavelength. Part 4, determine the energy involved. Okay, the energy here refers to energy change, delta E. Okay, you have delta E equal to H mu, Planck's equation, Hc O lambda. And also you have another delta E formula, which is a combination of Planck's and Rydberg's equation. Planck's equation and Rydberg's equation, which is RH 1 over Ni square minus 1 over Nf square. Ni and F. When you use this formula, it would give you either a positive or negative answer, depending on the initial, is it bigger than the final or initial smaller than final. Okay, so don't worry, the positive negative tells whether energy is absorbed or energy is released. So when we talk about line spectrum, definitely you get negative value when you use this formula because energy is released. So remember the energy here is delta E. Don't try to use this formula. This formula, negative RH, there's another energy formula, O(n) square. This is quantized energy of electron, at a certain energy level or orbit. There's no energy change, and the electrons circulating in the same energy level or orbit. So you don't find delta in front. All this delta are energy change here due to a transition. Transition means the electron changing level from high to low, low to high. So if you want to calculate the energy involved, must be formula with delta E. So inspecting what we have done so far, okay, you can use this or this. This one, we cannot use directly because this is frequency, not involved so far in our calculation. We have lambda. calculated here. So you can use this formula, or otherwise you can use this formula because Ni and F you know, initial 4, final 2. Okay, Ni and F follow the process. If electron drop, the initial must be high, the final must be low. If in electron promoted, or excited, then this is small, this is big. That is the difference, That is the difference between writing IF and 1, 2. This one 1, 2 here. 1, 2 forever, 2 larger than 1. IF follow the process. Okay, initial depending on electron promoted or fall. If electron fall, this is the case of electron fall, the I for big number, the F small number. You will end up getting a negative answer, which actually reflects energy released, or emitted. Okay, so I'll use this formula first. And this is the one that I've told you just now. You got two RH here. One is this, one is this. Because the title is energy here. So you choose the one with energy unit, the RH with energy unit. All right. Then this initial final follow the process. Line X just now formed from the transition of electron from n equal to 4 to n equal to 2 means this is the initial, this is the final, Okay, so substitute, you will get a negative answer. So this means energy release, or energy emitted. Or you can use this, as I said, Planck's equation, because lambda already known. Same answer. This one shouldn't have negative. I copy paste, forget to remove this. This one you get the magnitude only. Alright? But doesn't matter, you can, if to play safe, you put in bracket energy emitted. This one you don't need to write energy emitted, also okay, because the negative reflects energy emitted. But it all depends on you. If you want to play safe, then you write energy emitted here. Because the question here is energy involved. Alright. So these are the marks. One each. Okay, from equation, substitution, answer with unit. This one also equation, substitution, answer with unit. If here all, means this one also one each. If you use this method, also one each. So you have alternative formula to use. So chapter 2 calculation is actually very easy. There's only 6 formula. I have already written 1, 2, 3, 4 here, and then this one 5. Okay, the 6 is actually mu equal to C over lambda. Only these 6 formula. You play around with these 6 formula, you are sure to get the answer, Any calculation related to line spectrum or atomic Bose atomic model, Okay, I move on. 2B, describe the anomalous electronic configuration of chromium atom. So this is a very direct knowledge question. As usual, you have to write 2 configuration. Expected electronic configuration, actually this is based on Aufbau principle. Aufbau principle. Alright, the expected one is based on Aufbau principle. So you just follow Aufbau principle in filling electrons. 1s, 2s, 2p, 3s, 3p, after 3p, 4s, and 3d. Use up all the 24 electrons. But the actual one, is what that is really exists. So the expected based on Aufbau shows that this is not as stable 3d4, yeah. 3d4, if you sketch the energy in the orbital diagram, D got 5 orbital. 1, 2, 3, 4, 5 orbital. 3D. 4 means 1, 2, 3, 4. So there's one box without electron. Okay, or one orbital without electron. So this is termed as partially filled. Yeah? If it can get one more electron, if one electron from 4s, yeah, because the 4s is fully filled. If one of these electron can jump over here, the configuration will be having every orbital or every box will be having one electron in it. So that is described as half filled and it has high stability, extra stable. So from here to here is actually the jumping of one electron, yeah, from 4s into 3D. The purpose is to achieve half filled, yeah, 3D orbitals which have extra stability. Yeah, half filled is like this. You see, like this. So every orbital got one electron, so they will be happy, yeah. Okay, because 3D orbitals are degenerate orbitals, orbitals of equivalent energy. So if everything is equal, yeah, every orbital got equal number of electron. So in layman's term, we say that, you know, it is, they are happy, yeah, all of them are happy. Okay, so the orbitals are happy. Each one get one electron. If each one got that electron, yeah, they will also be happy. That is called fully filled, yeah. All right. So partially filled, fully filled, yeah, means the number of electron in each orbital the same, either single or paired. So that makes the configuration much more stable. All right. Another reason why the 4s orbital electron, yeah, can jump into the 3D is because the difference in energy is small, yeah, between 4s and 3D. The jumping can only take place if the energy difference between the orbitals are small. Okay, so electron cannot simply jump, let's say from 1s into 2s or 2s into 2p, cannot do that because the energy difference are big, yeah. So it cannot simply jump that way. It requires energy, yeah, to be promoted or jump. Okay, so that's the reason. Because of the difference in energy between 4s and 3d are small, one electron from 4s orbital jumps into the 3d orbital. The purpose is to obtain, yeah, or to achieve extra stability of half-filled 3D orbitals. So very simple anomalous configuration in your syllabus is chromium. The other one is copper. So you can refresh back, yeah, study back. Copper is the same thing, yeah. 4s electron jump into 3D, but then the 3D here is 3D9, here becomes 3D10 fully filled. Yeah? Okay, so this is very important to highlight half filled. Yeah, extra stable. So the marks 2 only. I think these two electronic configuration, 1 mark, and then explanation, 1 mark. So we are done with question 2, total marks 10. Yeah? And this is also the marks allocation for PS1. Yeah, chapter 2, 10 marks. Now I move on to question 3, which is chapter 4 question. Explain each of the following statement. Upon reaction with fluorine, oxygen forms OF2, whereas sulfur able to form SF2, SF4, SF6. Actually, without drawing Lewis structure, if you are quick enough to think, SF6, 6 fluorine around sulfur. That means around sulfur, yeah, there are total of 6 times 2, 12 valence electron. Okay, 12 valence electron. So can sulfur take 12 valence electron? Okay, if can, why? Yeah, things like that. So the reason here is because of the location. Yeah? Oxygen is period 2 element. It does not have d orbital. Period 2 element, the outermost shell n equal to 2. When n equal to 2, L equal to 0, 1. So orbital allowed to S to P. So these are the real orbital that can exist. If you fully fill, every orbital, this one 2, this one 6, total 8 valence electron. If got more than 8, there's nowhere to put because it does not have, at energy level number 2, period 2 element. It does not have d orbital. So it cannot accommodate more than 8 valence electron. So that's the explanation here. Oxygen being period 2 element, it does not have d orbitals. So the valence shell cannot accommodate more than 8 electrons, or oxygen cannot expand octet, in other words. Okay, maximum it can place 8 only, not more than that. Sulfur period 3 element. Period 3 element, n equal to 3. When n equal to 3, L equal to 0, 1, 2. 0 is 3s orbital, 1 is 3p orbital, and 2 is 3d orbital. If we were to fully fill every orbital with electron, maximum 2, maximum 6, maximum 10. So total it can take up 18 valence electron in bonding, in forming bonds with other elements. So this is far beyond it. That means it can expand octet. Okay, so this is very important. It has d orbitals in its valence shell that enable it to accommodate more than 8 electrons. 8 electrons, typo error. Or in other words, it can expand octet. Yeah, it can expand octet. So the importance of having d orbitals in the valence shell of the element, just by knowing where it's located in terms of period. Period 3 and above elements, period 3, period 4, and so on, they will have d orbital because of these quantum numbers here. Okay, that's the reason why you learn quantum numbers, to help you understand why certain atom, a central atom in a compound, can expand octet, why certain cannot, and why certain central atom have odd electron, have less than octet, and so on. All right, so you just have to refresh back, to refresh back your knowledge on this. So 2 marks only, one about oxygen, one about sulfur. Okay, so to highlight about orbital d, d orbitals. Period 2 having s and p orbitals only. So in bonding, we can only accommodate up to 8 valence electron maximum. Okay, I move on to the next. The shape of PF5 molecule differs from that of an IF5 molecule. Actually, this question missed out in your question paper. Okay, so you can add in this question. Now you can screenshot it if you want. So to talk about shape of molecule, you have to start off with Lewis structure. Number 1, you have to draw Lewis structure. This is draft for you. In the answer, there's no Lewis structure drawn. After that, you have to count total valence electron at central atom. After getting the total valence electron, we have to count how many bonding pair, how many lone pair. Total electron pair, not valence electron. Total electron pair at central atom. After that, you count how many bonding pair, how many lone pair. And then the third one, you get the shape or geometry. Shape or geometry. Okay. Total electron pair will give you electron pair geometry. You always start off by drawing electron pair geometry. Okay, using the central atom and lines. After that, you do away with lone pair, yeah. You take away the lines, you replace with lone pair, then what is left is the molecular geometry or shape. So if you follow this process, PF5, 5 bonding pairs, and no lone pairs, yeah. PF5. P 1, 2, 3, 4, 5. Okay, no space here. Actually, the first thing you have to count valence electron. Yeah, PF5. P equal to 5 valence electron. And then 5 fluorine, 7 times 5, 35. So the total will be 40. 40 valence electron. Then after drawing skeletal structure, you put the what you call octet on the bonding electron. Okay, put octet. Octet means pair up. Already got one line, so that means what you need to draw. Okay, you need to draw too close already, clashes. F 1, 2, 3, 4, 5, 6. The dot tend to stick to each other. Some problem with my stylus. Tend to easy stick. Doesn't matter. So you understand what I'm drawing. Yeah, I'm drawing octet around each atom. Yeah, bonding atom. So octet means 8. 8 times 5, 40. All used up already. And central atom already more than octet. So this is the Lewis structure. Yeah. So you inspect the central atom. Total electron pair 5. Okay, and all the 5 are bonding pairs. There's no lone pair. You have to inspect Lewis structure, yeah, to get this total electron pair. How many? Yeah, total electron pair first equal to 5. Out of the 5, 5 bonding pair, no lone pair. Then you start to draw 5, yeah. Electron pair geometry for 5 is trigonal bipyramidal. So all these are knowledge here that you must have. Bipyramidal. So you start to draw P, okay. 3 on the plane, like a Y shape on the plane, yeah. One above, one below the plane. And then you see there's no lone pair. No lone pair, that means you attach the bonding atom to all the lines like this. So the molecular geometry or shape is still trigonal bipyramidal. Okay, so the shape is trigonal bipyramidal is the drawing. You don't need to use this 3D. You can just use ordinary line. Okay, just use normal line. And then the same goes to IF5. You do the same, yeah? IF5. IF5. Valence electron iodine is 7. And then 7 times 5, 35, yeah? 7 times 5, 35. So total 42. Then you start to draw I bond to 5F. 1, 2, 3, 4, 5. And then give octet, yeah? Give octet to the bonding atom. I cannot do fast. If I do fast, it tends to stick one to another, the dot. Okay. Hmm. 1, 2. Okay. Because there's already one line, so you just need to put 3 pairs of dot and total 8. One line is 2 electrons. Something like that. So 1, 2, 3, 4, 5, 8 times 5, 40. 2 more will go to central atom. All right. So total electron pair, total electron pair at I, you must always look at the central atom. Okay, 5 plus 1, 6. Out of the 6, 5 are bonding pair, and then 1 lone pair. So 6 here, electron pair geometry is octahedral. Octahedral, so you draw octahedral. Okay, octahedral is 4 on the plane, atas satah, yang 1 above, 1 below, atas bawah satah. And then you see 1 lone pair. The lone pair, you take out 1 line. This is the best position. Actually, anywhere also can, but this is the best position on paper so that the remaining shape can be described easily. Okay, and then put in bonding atom. The remaining lines you put in the bonding atom, so the shape appears. So this is a square planar. Square planar, The square pyramidal, sorry. Square planar don't have this. Okay, square pyramidal, because when you connect them, you see it's a pyramid, square pyramidal. Okay, so that's how you do it. You have to inspect restructure, and count total electron pair at central atom. This one also just now at central atom. The total electron pair will give you this electron pair geometry, this one. You start to sketch electron pair geometry. After that, you remove the line, replace with lone pair, if there is lone pair. Then the remaining line, you bond the bonding atom. Okay. So the marks, it's the mark. You can actually write total electron pair, then how many bonding pair, how many lone pair, doesn't matter. Like this, I mean, is more appropriate. But the marks, they just look into bonding pair and lone pair only. Sometimes the total pair also considered for marks, so it's best to write everything out. Total electron pair, how many bonding pair, and how many lone pair. It's best to write it out. Okay, so when you talk about shape, different, your explanation is to explain starting from inspecting Lewis structure. The Lewis structure you draw, so it's okay. Since you need to draw, you just draw on your answer sheet. Doesn't matter even if marks is not given, because you need it. You need it to count the total electron pair, bonding pair, and lone pair at central atom. Okay, so since I'm showing you where the marks are here and you don't see marks for this structure, don't worry. In exam, you draw it. Because this question, they will allocate mark for Lewis structure. Probably other question, next time when appear in your PS, there's mark for Lewis structure. So you do not know what is going to be allocated marks. So as long as the process, where the process is concerned, just write it down. Because if you don't write down on your answer sheet, you still need to scribble somewhere on your question paper or a paper. So might as well you write down on your answer paper. Okay. Question 3A2. 3A3. Actually, in your question paper 3A2, but it's 3A3. As I said just now, the question that I've just discussed about the molecular shape is missing in your question paper. Okay, of the 3 possible resin structure below, the structure 3 is the best structure, this one. So explain each of the following statement. It looks like the former charge, these are all former charges. Already shown in the question. Former charge, if you have to calculate yourself, Okay, then you need to calculate. Normally, if you ask to find the best Lewis structure, the most plausible, the most stable, then you need to be based on formal charge. So if it's not given in question, you calculate yourself. So for this question, it's easy because given already. Okay, how to select the best structure or the most plausible structure from a several Lewis structure. Okay, the lower, the better. So if you see this is high because it involves 2 here. So this is the first thing we can eliminate. Out of these 3, this one has highest formal charge, highest formal charge. So this is the one that we would remove first or eliminate from our choice. Left these 2. These 2 looks like the same, 0, 0, minus 1. This one also 0, 0, minus 1. So when you have the same Lewis formal charge, what you need to do is to look at the negative formal charge, where it resides, where is it located. So for the first structure, -1 on nitrogen. This one, -1 on oxygen. If you compare electronegativity, electronegativity, electronegativity. O is more electronegative than N. So the more electronegative atom should bear the negative formal charge and that structure will be stable. So that means the third one. So that's the reason and you explain based on electronegativity. 3 is the best structure. Actually, I don't think this one got marked because it's stated already 3 is the best structure. Structure 1 and 2 have lower formal charges than structure 1 and 3 have lower formal charges than 2. As what I said, this is high. So between 1 and 3, negative formal charge in structure 3 resides on the O atom, which is more electronegative than N atom. I don't think this is given mark. This shouldn't be given mark because it's already in the question. 3 the best structure. I think somewhere it goes wrong. By right should be saying which has lower. Think should be this one. Okay, 1 and 2 have lower formal charges than structure. 1 and 3 have lower formal charges than 2. But comparing 1 and 3, both have the same formal charges. 3 is better because the negative formal charge resides on more electronegative atom O. Okay, A done. So this have to refresh here about formal charge. I hope you know how to count formal charge. Formal charge, just revise lah. Formal charge equal to number of valence electron minus number of bonds plus number of lone electrons. That means you just count the lines and count the dots, on the atom. Formal charge is for atom, every atom got a formal charge. Okay? For example, like this. So the formal charge, you must have knowledge lah. Oxygen is 6 valence electron. Then you just observe around it, got 2 lines, isn't it? Number of bonds. How many dots? 4 dots, like that. Okay, number of lone electron, you just count the dots. Count dots, don't count in pair. Count 1, 1, 1, 1. So the answer is 0. 0. Just have to refresh lah what you have learned. This is the easiest formula. Okay. Count the lines, count the dots around that particular atom that you want to count the formal charge. But this one you must have knowledge, You know where the location is in periodic table, then you know the valence electron. So even though periodic table is not tested, a lot of things you learn there is required, in other chapter. Like this, for example, electronegativity, valence electron, Okay, I move on to the next part B. Illustrate the hybridization of central atom in SF6 using orbital diagram. Okay, we do this first part first. And the second part, this one, on another slide here. So this is actually called hybridization process, if they said using orbital diagram. So you have to show ground state. Again, you must have knowledge here. Sulfur is period 3. Okay, that means the valence shell will be 3s, 3p, 3d. Yeah, the valence shell will have all these orbitals. But then, you also need to know valence electron, yeah? So it's group 16. So how many valence electrons? 6 valence electron. So actually, before you start doing this hybridization process, you need to know the type of hybridization. So you draw the Lewis structure for this. Yeah, Lewis structure. Okay, total valence electron 6 plus, yeah. Sulfur 6. Fluorine 7 times 4, 28. So total 34. So when you start to draw, S, 1, 2, 3, 4. You know why we need to do this? Because after that hybridized state, you must know the type of hybridization, yeah? Okay, so I put it slower so that it won't stick, yeah, to each other. All right. So by giving octet, yeah, that means 8 times 4, 32. Got 2 more. 33, 34. Put on central atom. So if you count total electron pair is 1, 2, 3, 4 plus this lone pair, 5, yeah? 5 electron pair means the type is sp3d. Okay, 3 plus 1 plus 1. So 5, yeah? sp3d. And then now you can start doing. Okay, so just now you know period 3, you know how to label the orbital, yeah? 3s, 3p, 3d. This one also must have D, tertinggal. Starting from ground state itself must have the D. Didn't notice it's missing here. 2. Okay, 3D. 6 electron here. Follow above principle. 1, 2, 3, 4, 5, 6. Here, Hund's rule. Yeah? Follow Hund's rule. Don't forget 1, 1, 1, then pair up. So total 6. And then because the type is sp3d, yeah? That means one of these yeah, actually excited to this. One of it excited. It involves 1D only. So you have excited state where electron of 3p jump into 3D. So you come up with this. So now you see 1, 2, 3, 4. Yeah? 4 single electron can make 4 bonds. So it complies the Lewis structure. If the ground state only 2 electron can make bonds, cannot explain the 4 bonds here. So after excitation, yeah, because the type is sp3d, so you just split this, go into 3D orbital. So you come out with 4 single electron. This type of single electron can be shared, yeah, with another 4 electrons from other atom. So as in the Lewis structure here. Yeah, later it can be shared with the fluorine. Okay, and then hybridized state. sp3d, you must draw 5 boxes. Yeah, all hybrid orbitals are degenerate. Yeah, equivalent energy orbitals. So the boxes must be joined up. Yeah, boxes mesti cantum. If got gap means different energy. Yeah, if join up means same energy. This is called what you call degenerate orbitals. All hybrid orbitals are degenerate orbitals. Then you label sp3d, electron just follow. Yeah, arrangement of electron just follow only the excited state. And this is very important. Yeah, to proceed with the next. The next you're supposed to draw orbital overlapping. Yeah. Okay, marks first. 1 mark, 1 mark, 1 mark. So actually, you have to show D, yeah, as early as ground state. You have to show D as early as ground state. Yeah? but it's still empty. But you have to show it, yeah, to show that it is available, yeah, or the sulfur has that 3D orbital, but it's not filled with electron. Okay, next we're going to do the second part. Yeah? Show and label overlapping orbitals. So I bring the hybridized state here. This is how you should do. You must know the shape. sp33 is trigonal bipyramidal. 5 electron pair or 5 hybrid orbital trigonal bipyramidal. Okay, so you have to draw trigonal bipyramidal. I roughly sketch here first. Later it will appear. When it appears, all in already. Trigonal bipyramidal. 3 on the plane. 1, 2, 3. Actually, the orbital must be of the same size. Same shape, same size. 4, 5. One above, one below. Then you must label sulfur. Okay. And then you put in the electron. When there is lone pair, you must put it on the plane. Lone pair put here. Okay. The rest are bonding pair. Single electron ready to be bonded. After that, you look at this just now. I've already drawn the Lewis structure. The Lewis structure just now, like this, something like this. And then this one all got dots around now because octet. Just now it looks like this. Okay, so there's one lone pair. This is the lone pair. And then the 4 bonding pair, fluorine will use, because fluorine is p block element. So it will use p orbital, POP. Okay, so you just put dumbbell shape, and then you must label F, and then you pair up the electron, and then you must label 2p. How? Alright, same goes to here. You have to put the dumbbell shape, label the atom, pair up the electron, and label the orbital. All orbitals must be labeled. This one also same thing. Put F here, 2p orbital, and then pair up electron. This one also same thing. Okay. It should be more or less the same size line. Cannot be too big or too much smaller. Fluorine, 2p, and then like that. Okay. This one also must label sp3d. That's why you need to draw big, sp3d. Draw a bit big the loops. sp3d. sp3d. Label lah semua. sp3d. So it's complete now. What you need to label an atom. The shape must be proper, trigonal bipyramidal, dumbbell 2p, and then the atoms must be labeled, and then the orbital type must be labeled 2p sp3d, and then the electrons on the overlap region. If there's lone pair is the one that you label first, because trigonal bipyramidal, the lone pair must be on the plane. Cannot be above or below the plane, must be on the plane. Either here, or here, but this is the most strategic. Okay, so if you are asked to describe the shape, this is actually seesaw or distorted tetrahedral, but this is not needed in this question. So that's how it looks like. This is what they call, no animation, everything come out already. Cumanya dia label F dekat situ. Patutnya F you normally label at the center here lah. We normally label at the center here. Okay, that's better. Okay, so you have to draw it big. This one also label kat dalam. Okay, the marks. All labels correct. Means this one sp3d, 2p, atom label, fluorine, sulfur, and then orbitals and shape correct. That means it's dumbbell shape, and this is trigonal bipyramidal shape. That's how the marks bundle up. Okay, a lot of things need to check, then you get one mark. This one also need to check the shape of sp3d, shape of 2p orbital, then you get one mark. All right, done. So this would help to refresh about orbital overlap. Every time you want to do hybridization process using this orbital diagram, you must inspect which structure first because you need to know the type. You need to know the type, Even though in the answer dia tak tulis, but you have to do it. Otherwise, you get stuck, you tak boleh proceed. Okay, you must start with which structure because you need to know the type of hybridization before you do the S, ground state, excited state, hybridized state. Without this, you cannot. Because excited state also you need to know whether it involve D or not involve D, then the electron will jump into D and things like that. Okay. C. Last one. Explain the difference in melting point between element of in group 1 and group 17 of the periodic table. Okay, you know group 1 elements are all metals. So the bonding involved when you talk about melting or boiling point, what you need to do is inspect the bond. Inspect bonding type. If it's metal, of course they are having metallic bonds. Okay, you learn two models, electron C model, energy band. All right. Group 17, you know they exist in the form of molecules. Chlorine, bromine, iodine. So between one molecule and another molecule, they are simple covalent molecules. So you have the so-called van der Waals forces. So in melting, this is what you overcome. Van der Waals forces. Whereas for metallic bond, if you talk about electron C model, for example, okay, electron C model, I just simply sketch one example here. Na plus, for example, Na plus, Na plus. Okay, per atom release one electron. So what is metallic bond? Attraction between the cation and the delocalized electron. So that is called metallic bond and you need to overcome that. In bonding, you need to overcome the attraction between the cation and the valence electron. Okay, so this involve plus minus attraction very strong. This one involve partial plus, partial minus. Okay, London forces partial plus, partial minus. Okay, if you learn, if you recall back what you learned, chlorine, is actually non-polar. But then the in between, they have that so-called London forces. The type of van der Waals forces is London forces, which arise due to random movement of electron and it generate, what you call the partial plus, partial minus n, which will attract each other between neighboring molecules. Okay, so when the attraction involving partial charges is weaker, the attraction. Whereas this one full charges, is actually attraction between the nucleus, and the valence electron, nucleus of the cation. Okay, so full charges attracting each other very strong. This one partial charges, weaker. Okay, so pentalic bond is stronger than van der Waals forces for that reason. If you want to know in detail why, okay, because it involves attraction of electron and nucleus, which is proton, very strong attraction. This one partial charges, plus minus, partial plus, partial minus. That's why metallic bond stronger when the forces weaker. So more energy needed to overcome the metallic bond. And we can conclude that the melting point of group 1 elements are higher than group 17. Much higher, Okay. This is primary bond. This is secondary bond, bond between molecules. Okay. This bond between atoms. So very strong melting point, high. So when you talk about melting or boiling point, always inspect the bonding type. It can be primary bond, covalent bond, ionic bond, metallic bond. Or it can be intermolecular forces, which is called secondary bond. It will be van der Waals forces, hydrogen bond. And you already learn, in comparison, generally, secondary bond, or intermolecular forces are 25%, the strength of primary bond, so they are weak. Okay, so that's all. Total marks 17 supposedly, yeah. But I think if include the one missed out, yeah, the question is more than 17. Doesn't matter. Okay. Our purpose today not only about marks here, but it's more of like helping you to revise, yeah, to refresh. If you find that most of my explanation you cannot understand, it means you are not prepared yet, yeah. You are not prepared yet. But if you find that my explanation makes you understand better, that means you are already prepared, at least you're 80%. So the marks here, 4, saying that group 1 have metallic bond, group 17 van der Waals forces between molecules, comparing strength and the energy needed to overcome, and finally reduce or generalize, yeah, which has higher boiling point, melting point, or which has lower melting point. All right, that's the end of this week score. Yeah, you can always be better. There is no substitute for hard work. Yeah, I always believe in no substitute for hard work. Yeah, wait, this one. No substitute for hard work means hard work is needed. Okay, you should have already worked hard throughout the semester, and at this point, at this juncture, you actually should be working smart as well. Yeah, hard and smart. The hard work should be consistently throughout the semester, but semester is almost ending, so you reflect on your own self, yeah, whether you have been working hard consistently or not. If not, I think in these 2 weeks you still can catch up. Yeah, so try to catch up. Try to sacrifice whatever you can. Okay, so that's all for today's score program. I need to give you the link here. Hold on, yeah.
Thank you, madam.
No, don't leave first. I need to give you the attendance link. Hello, everybody. You cannot leave.
Thank you, madam. You are the best.
Okay, madam.
Hold on, yeah, don't leave first.
Thank you, madam. Let us wait.
You're still there, right?
Madam.
I want to give you the link, my dear. Where is the link? Link ni. Bukan. Wait. Pembelajar yang tembak Google Meet. Sila join link ni. No, this is not the one. Hold on. Sorry for waiting. Sabar, sabar, sabar.
Thank you, madam.
Okay, jangan lari dulu. Hold on ya. Wait, kejap ya.
Madam ada recording ni tak?